So today we look at trig functions, understanding trig functions. So we have a lot of review today to cover some things that we did last year in pre-calculus. I think we'll begin with maybe a quick review of that circle. Let's see if we can get it so it's not filled in with a color. Well, I guess that'll be okay. And let's do this and this. When I say trig functions, and I'm thinking review, I'm thinking we need to understand the relationship between between degrees and radians. So let's identify these really quick. We'll go red as our 45, so that's 45 degrees. This is 90 degrees, of course. This is 135. This is 180, 225, 270. Ooh, that doesn't look like I put that in a very good spot. I gotta fix that one. Try that again. 315 and 360, which is also then our 0 degrees as well. How about radians on those? You guys remember them? Pi over 4, pi.
No. Pi over 2.
What am I doing? Yes. I was listening and writing it. I heard you say pi, and I'm like, oh, that we're going around. Pi over 2. 2 pi over 2, 3 pi over 4, 4 pi over 4, 5 pi over 4, 6 pi over 4, and I'm reducing these, 7 pi over 4. And then we identified 30 degrees. So here's our 30 degrees. So here's our 60 degrees. And when I'm saying that, of course, we're measuring it from here, correct? So this is what I'm looking at when I say 30 degrees. 90 degrees. 120, 150, 210, 240, 270, 300, and 330 degrees. So my radians that go with all those, you remember 30 degrees? You remember what that one is? Pi over 6, pi over 3, which is 2 pi over 6, 3 pi over 6, 4 pi over 6, 5 pi over 6, 6 pi over 6, 7 pi over 6, 8 pi over 6, we'll write that as 4 pi over 3, 9 pi over 6, 10 pi over 6, we write 5 pi over 3, and 11 pi over 6. When we're doing this, we spend a little bit of time and we talk about two types of triangles as well. We have our 45, 45, 90 triangle. So we know if this side is A, this side is A, this is A roots of 2. And we also have our 30, 60, 90. So that's 30, that's 60. So the short side is A, the long side is twice that. This side is A roots of 3. And the reason I do that is I'm going to jump to the next screen and we're going to write down the nice angles for the sine, the cosine, and the tangent. Maybe we should add a few more things here. This is a crazy day. We're just doing all kinds of stuff. We know that the sine of an angle is y over r. The cosine of an angle is x over r. The tangent of an angle is sine over cosine, which is y over x. When we talk about right triangles, we talk about opposite over adjacent. For the tangent, for the sine, we talk about opposite over hypotenuse. For cosine, we talk about adjacent over hypotenuse. We also then should jot down a few more things here, I suppose, like the cosecant of an angle is 1 over the sine of the angle. The secant of an angle is 1 over the cosine of an angle. And the cotangent of an angle is 1 over the tangent. So those are the reciprocals. So, of course, I could write cosecant, then I could write r over y instead of y over r. But I'll just leave it like this. I'm not going to go back and write those. And we decided when we did this that if it doesn't matter what size circle we talk about when we're looking at a ratio, so we're looking at something like this, and if I wanted to look at an angle, so there's my angle theta, if the sine of that angle is y over r, it doesn't matter which triangle I look at, so to speak. If I do this, where our y value, of course, is that dotted one I just brought down, and our r is the distance to the edge of the circle, kind of that radius idea. If it doesn't matter which one we use, because they're all the same ratio, the fraction would be the same for all of them, then we decided that we should use a unit circle. Does that make sense? A unit circle, my radius is 1. So if I go back here, this distance would be 1. So in terms of my 45, 45, 90 triangle, my 30, 60, 90 triangle, we're then going to set this up so that our hypotenuse is 1. And that'll allow me to get, if I were to bring this down right here, I don't want to mess up this picture too much, I suppose, but there's a 30, 60, 90 because this angle is 30 right here. This is 90. If the hypotenuse is 1, then the shortest side is a half. This side is, you remember it? Square root of 3 over 2. Why am I drawing a blank? Is that right?
Well, it's just a root of 3. No, it'd be 1/2 root of 3. Square root of 3 over 4.
If this is a half, this is 1/2 times square root of 3. Root 3 over 2. We're good. 1/2 times root 3 is root 3 over 2.
Why did you say over 2?
Why did I say over 2? I was just questioning myself. Okay, let's get to, man, I thought I was just going to jump right into this table, and we're still a long ways from this table. When I'm talking about the table, remember when we did something like this, the sine of an angle, the cosine of an angle, and the tangent of an angle. And we need to do it for the following. I suppose 0. Yeah, we'll say 0. We'll say 30 degrees. We'll say 45 degrees. We'll say 60 degrees. And we'll say 90 degrees. And in addition to that, I suppose I think it'd be worthwhile for me to jot down that this is pi over 6, pi over 4, pi over 3, and pi over 2. And of course, this is still 0. Almost 100% of the work we're going to do in calculus is in radians. So make sure you're working in radians on your calculator. I always bring up the story of Tim Vo. He got done with this test. Tim Vo is working on his PhD at University of Nebraska right now. He got a chemistry degree, and he got done with this AP Calc test. His English skills weren't very good, but he left his calculator still, or average actually, because it's such a hard language I think for him to pick up. But he had his calculator in degrees, but he still passed the calculus test. But he knew he must have missed some by doing the calculations wrong. So I'll tell you this now, and I'll tell you again. Make sure your calculators are in radians on test day. All right, so what do we have for the sine of 0? Y over r. Well, I could also do this, because I don't know about you, but this is how I like to think of the sine. I'm all over the place right now, and I apologize. But that's our sine curve, right? Where our period is 2 pi. There's pi. How high does it go? 1. How low does it go? -1. Our cosine curve looks a lot like it, but we started at different spots. We still are going to go to 2 pi. Pi. This would be at 1. We're at -1. If you graph both those at the same time, you could see that you would get, if you took your sine curve and pushed it to the left pi over 2 units, you would get your cosine curve. Okay. So we can talk about domain being all reals, range being 1 to -1 inclusive. My period is 2 pi. So if I think about the sine of 0 is 0. If I think about the cosine of 0, here we are at 0. Cosine of 0 would put me at 1. Tangent is sine over cosine. I don't have a graph of the tangent, but that would be 0. Sine of 30 degrees. Sine of 30 degrees, if you look at your picture here, that's kind of a little bit hard to see because there's 45. It would be about right there. We find that it's a half, but remember why or where we're getting that half? If I were to draw my triangle and say that this is 30 degrees, this is 1 because we're talking about a unit circle. This is a half. We said this is root 3 over 2. Y over R, a half over 1. A half over 1, of course, is 1/2. We'll stay with that one. Let's do a 45-degree triangle really quick. This is 1. This would be root 2 over 2 then, wouldn't it? Somebody knock? Thank you. And this one would be root 2 over 2. So my sine is y over r, so it's root 2 over 2 over 1. So back to filling in our chart. This is root 2 over 2. 60 degrees. Let me just make another quick triangle here. So now this is 60 degrees. This is 1. This would be the shortest side, so that's a half. This side is root 3 over 2. It's a lot like this triangle right here, isn't it? Except we turned it. So y over r, root 3 over 2 over 1. And finally, at 90 degrees, our sine is 1. As a decimal, I think it's good to kind of have decimals in your head too. Back when we used to ride horse to school, because we didn't have cars, we had to use tables to look trig functions up. We didn't have fancy calculators like you guys have. So we'd look in the back of a book for a table and look at sine of 45 or the sine of 60. And I think it is still beneficial to have in your head how much square root of 3 over 2 is as a decimal. So punch that into your calculator. I'd like you to kind of recognize that that's 0.8660. Are you with me on that? And root 2 over 2, if you see 0.707, you should think, oh, that's root 2 over 2. So be familiar with the decimals on those. The cosine, you guys remember the relationship between the sine and cosine? If the sine of 30 is a half, then the cosine of what is a half? 60. They're co-functions. 90 minus 30 is 60. Likewise, the cosine of 30 would be root 3 over 2. And the sine, or the cosine of 45, they're both the same. 45 minus 45 is still 45. And at 90, we're at 0. And the tangent, the easiest one to remember, of course, is the first one. And I think this one, if you're ever asked to do the tangent of 45 degrees or pi over 4, you know that's 1. This one, sine over cosine, you can't divide by 0, so we know that this is undefined. When we look at a graph of this in a minute, you're going to see that vertical asymptote on your calculator. And we could also spend a little time. I'd like you guys to play around with that graphing app that's on your iPads. I looked at somebody's earlier today, but they're in Math 10, so we were graphing lines. I'd kind of like to have you guys look at that. Maybe not right now, I don't know if we have time, but mess around with that a little bit, okay? I'll do it on the other's calculator. Finally, the ones I don't memorize, and maybe I should, I think you have to we don't have to memorize the sine and cosine, but it's good to have them in your head and kind of quick. But I don't always memorize my tangent because I know I can get it. It's the sine over the cosine. Sine over cosine. So if I do this one divided by this one, a half divided by root 3 over 2, you multiply by the reciprocal, you can get 1 over root 3. 1 over root 3 is root 3 over 3. Likewise over here, sine over cosine, root 3 over 2 divided by a half, multiplied by the reciprocal, you're going to get root 3. And my problem for me personally is I remember it's root 3, and one of them is root 3 over 3. I just never remember which one. Why do we only do quadrant 1? Because of reference angles. And what did we say about reference angles? I think maybe how we wrote it was, you know, how far from x-axis. Something like that. How far from the x-axis. And then you reference everything back to an acute angle that would be in quadrant 1. So let me give you an example. We have something like this, and we're looking at this angle right here, and let's just say this angle is 135 degrees. And you want to know what's the sine of 135 or what's the cosine of 135. I'm working in degrees. I should be working in radians, but that's all right. How far from the x-axis is it? So what I want you to do is you think about doing this. So if that's 135, then this, of course, is 45, right? So we know that it's going to reference to our 45-degree angle. We're in quadrant 2. We have this saying that we learned last year, all students take calc. What does that mean? Which one is positive? So they're all positive in quadrant 1. Quadrant 2, the sine. And if the sine is positive, so is the cosecant, because it's reciprocals. Quadrant 3, the tangent is positive. So the cotangent will be positive, and in quadrant 4, the cosine is positive because it deals with x's. So in this case, if I wanted the sine, I know if I'm referencing to 45, so this would equal the same as the sine of 45 degrees. This would be the opposite of the cosine of 45 degrees because we're referencing it back. So in this case, root 2 over 2, negative root 2 over 2. So we understand reference angles. Okay. As I said, I've been kind of all over the place. We also know that the sine and cosine are periodic. We've talked about that. Let's glance at a couple of pictures of these things on our graphing calculators. So I've got some stuff. What's that? Blurry. So if I graph sine of x, and I'm going to set my mode. I want to make sure my mode is in radians. I'm in degrees. I'm going to go radians. So we say our window, you know, maybe what I want to do on this one is go negative 4 pi to 4 pi. So we'll see a few periods of this thing. My scale, I like to go by pi over 2. My y min, I think I'll just go to negative 1.5. We know it goes to negative 1. I'm going to go up to 1.5 so it kind of fills up the whole screen. And I'll go by ones. So there's my sine curve. And what I drew on the board, of course, was only one period, so I only drew it from 0 to 2 pi. I just show that because it's good to see more than one period, I think. If I do the cosine, and I'll graph that one on the same one, but I'm going to make it bold when I'm done. So I'll go over here and make this bold. And hopefully we can see, you know what, they look identical. It's just that one was in a windstorm and got pushed over a little bit. And you could push either one over. You know how you define a rhombus, right? What's a rhombus? It's a square that a fat guy leaned on. And we could say the same about these curves up here. You know, a chunky person leaned on one of them and it just slid it over. It's a shift is all it is, and we're going to talk about shifts in just a little bit. Leads me to, might as well continue with the mode of being all over the place. Remember when, let's say you graph something, and this is what you come up with. We did problems like this that dealt with tide. You could talk about the moon. You could talk about temperatures. A lot of things will look like a sine curve. There's also then sine regression on your calculators. When you do regression analysis, you'll see a sine one on there. I don't know if you'll see a cosine. But we said that you have a choice. Do you want this to look like a sine curve or a cosine curve? And write your answer. And I think you have a choice quick review on how we do that. If you know where the middle is, if you could get, well, I guess we'll say this point. Do you agree that this right here, if I were to find that point, that this right here looks like a sine curve? And if you do, the shift would be 0, 0 to, I'm just going to label this A. It's too hard to say exactly what that is, where that middle line goes through your curve. If you can find A. But the hard part when we did our problems is it's hard to find A. And by the way, you could have gone to this one instead. If you would have gone to this point, how would you define that curve right there? If you would have found this one, what would you have to put in front of your amplitude? If instead of going like this, you start here, isn't that just the sine curve going down first? You need a negative sign in the front of it because it's the opposite. You just heard me say the word amplitude. I don't want you to get confused with this. This isn't amplitude. This is just a point A. Amplitude, recall, is max minus min divided by 2. So our amplitude on the curves that I have on the graphing calculator both are 1. 1 minus a negative 1 is 2. 2 divided by 2 is 1. If you think about it this way, the amplitude will always be the distance from this axis to the highest point. It'll also be the distance from the axis to the lowest point. So that's in terms of sine. If you ever want to do this, shift and write it in terms of cosine, and we found that easier. And the reason we found that easier is oftentimes we knew the highest point. If you know the highest point, or the max, the shift for cosine, this is for sine right here, the shift for cosine is 0a, and now I'm talking about amplitude. 0a to the max. So if you know what the amplitude is, let's say, I don't know, let's just say it's 2, 0, 2, then your shift would be right there. We're going to get into shifts here in just a little bit, but okay. Look at that on the screen. Is that part of the sine or part of the cosine? It's still alive. It was like sunning himself on his back. That was weird. Little fly. Little itty bitty fly. Well, you know what? Let's stay with this. Let's talk about shifts. And if you want, you can have your iPads out trying to graph these as well. The sine curve. I know grabbing it's pretty slick. Although I found that I couldn't get it where I wanted sometimes, so I want you guys to teach me a little bit about it. Graph equations. I think there's equations on the top. So you go up here, and let's delete that. So let's say you want to graph the sine of x. And then I think you say save. Oh, what's the... And then I just noticed if you do this, you can zoom in. You can pull it this way. I think you can pull it. I got a little frustrated though with the shape of it. You know, if you grab it like this. But you can always reset it. This, and then you can pull it. You're changing your.
Oh, look.
You can pull it this way, I think.
Check this out.
And you can quick reset it if you want.
Oh, how did I make it like that?
But I would sometimes like to be able to just type in what I want to look at rather than sit and trying to drag. But you change your x-axis, your y-axis. You can really change the looks of it.
Oh, yeah, now I get it back, though.
So I would like you guys to teach me a little bit about this. So mess around with it. Have some fun with it.
How do you change like the axis? How it goes by?
I don't know.
With your fingers.
Yeah, just your fingers as far as I know. I don't think you go to your window like you do on the TI 84. But sometimes I can't get it where I want it. Sometimes it's like I just know where I want to look, and I can't get it where I want to look.
Whoa.
But it is color, and that's nice. And I would like to graph on the calculator one more up here. I didn't graph the tangent, and you guys can graph the tangent on there if you want. I'm going to change my windows so it's a little more than this, because we need to talk about tangent as well so we understand domain and range, how it compares to, how it differs from. So here's my sine curve. If you want to just look up here a second, I probably could get that cosine curve off of there. But remember, we have vertical asymptotes, so the tangent looks something like that. It has places where it doesn't exist, so you don't actually see the vertical line asymptote, but it doesn't exist, of course, where the cosine is 0. So anytime you see that really heavy 1, 0. And the reason it takes off is you take a number that gets close to 1 and you divide a number by that's really, really small, really close to 0. So 1 divided by 0.1 is 10. 1 divided by 0.05, right? So then it blows up. So the range on that would be all reals, but the domain isn't. We have problems at, what, pi over 2? And then pi over 2 plus pi. Okay. How about the, you guys remember what the secant looks like? Let me take this one off. Let me just shut that one off. How would I graph the secant? I'm going to turn off the cosine as well. The reciprocal, 1 divided by, in this case, 1 divided by the sine of x. The cosecant. If I graph that one, I've got a few more, too many periods. It takes too long. But remember, it looks something like that. I would say the period of that is 2 pi. But we still have vertical asymptotes because we have places where the sine is 0 and it can't be 0. If your calculator doesn't look like that, you might have the mode set. What do I have mine on? I have mine connected. Sometimes you go dot. I'm not sure, but sometimes you'll see like a vertical line show up in there, not part of your graph. How would the secant compare to this? To the cosecant? Instead of the sine curve, you're just doing it on the cosine curve, right? So it kind of looks the same. Your range on this one would be 1 to infinity, unioned with -1 to negative, or negative infinity to -1, unioned with 1 to infinity, including the 1. And again, we have problems with the domain at these places like 0, pi, 2 pi, etc. Okay? How about, if you think about all these curves, we've discussed just a little bit about even functions and odd functions. One day last week, I think. What is a function? How do you know a function is even? What did we talk about for the symmetry? For an even function. Where is there symmetry, or what is the symmetry? Symmetry on an even function is the y-axis. So do any of the trig curves have symmetry on the y-axis? If you folded it over, would you get the identical picture on the y-axis? Is that one going to work? I always start like that. If you folded that one over, would it work? You bet it would. So what's even would be the cosine, and I'll just use theta. And if cosine is even, so is the secant. What can you say about the sine? If I were to run a line through the origin, you see that that distance equals that distance. It has symmetry. Odd has symmetry. It has a point of symmetry with respect to the origin. So what's odd would be the sine of theta, so the cosecant of theta. Likewise, if we look at a picture of the tangent of theta and the cotangent of theta, we would see that they have a point of symmetry with respect to the origin. I was so excited to begin the hour, and I wanted to get to that table that I was just jumping all over the place. Let's back up just a little bit, and let's talk about how you find arc length. Arc length. Because it really ties into radians, so I kind of skipped over that a little bit, and maybe we can do all that because we know all this is review for all of you. If you have a piece of pie, so to speak, and our central angle is theta, and this is our radius, and this is our arc length. When I'm talking about our arc length, I'm talking about this piece right there. That is our arc length. Does anybody remember the formula for the arc length? S equals r theta. That is when theta is in radians, correct? If we're in degrees, we know we could just do theta divided by 360 and then multiply it by the circumference, 2 pi r. But in this case, nice and easy, we're working in radians, S equals r theta. So the special sector that I would like to discuss, so we can kind of visualize this a little bit, is when theta equals 1. I'm talking about 1 radian. If I'm talking about 1 radian, that means, if you think about this formula just a little bit, if I'm talking about 1 radian, that means that this arc length S and the radius are equal to each other. So if you can picture this, if the arc length and the radius are equal to each other, that means this inside is 1 radian. Does anybody remember how much 1 radian is about in terms of degrees? And I do this because our minds are so ingrained on degrees. All those skateboarding guys, you know, they're doing 540s and 720s. They don't ever say we're doing 2 pies and 4 pies. Be great if they did. Do you know a great skateboarder? No. Snowboarder, maybe. 1 radian is, if you looked at my picture, I think I would say, well, you know what, it looks like it's about 60 degrees. Knowing what 60 degrees looks like. It's not exactly 60, though. Who has it?
59.7.
What's 180 degrees divided by pi? And the reason I can do that is because of that circle we did at the beginning. What's 180? Because we know that we know that pi radians equals 180 degrees. So if you want 1 radian, that would be 180 divided by pi. 57.3. I just remember that it's around 57 degrees, 1 radian. So it's kind of a nice thing to have in your head. So if you ever see, you're working into radians, and they ask you the sign of 2. Can you kind of visualize where the 2 is? Well, I think if you go back to this circle, I think you can kind of visualize 2, because do you know how much this is? Pi is 3.14. Do you know what pi over 2 is? What's half of pi? Plug it in so you know it in your head. Half of 3 is 1.5. Just a little bit more, 1.57. So if I'm talking about 2 radians, I know I'm between 1.57 and 3.14, right? So you know you're in quadrant 2. How about if they said the sign of 3? What quadrant are you in? If they just wanted you to find out if it's positive or negative. Sign of 3. Now they don't say anything. They don't put a degree symbol. Radians. You know you're just a little bit above this, right? A little bit above pi. This is where it gets, I think, a little harder, is down in quadrants 3 and 4. We know this is 6.28. We know this is 3.14. Do you know how much this one is? You're adding about 1.5 to 3. So you know it's around 4.5, right? A little bit more than 4.5. 4 point, what do you say? 7.1. Okay. So if they said 5, and they asked the sine of 5 or the cosine of 5, let's go cosine this time. Would the cosine of 5 be positive or negative? What quadrant are you in? You're in quadrant 4, so it would be positive. Okay. We still have one last thing to kind of tie back into, and that's going back to that shift. I kind of previewed it a little bit here. Let's talk about in general shifting. In general shifting. So if you have y equals a times the quantity, we'll use sine I want to use the same notation that's in your book. 2 pi over b times that quantity x minus c, parentheses, bracket that, plus d. And maybe before we walk through that one, I think we maybe should take a second to walk through this. Let's walk through this one first and talk about what's happening on this. The A, this right here, vertical, stretch, or shrink. We talk about, and we think of that word as amplitude when we do sine and cosine, but right now it's like pulling it up or down. So we have a vertical, stretch, or shrink, and that also affects the reflection, depending if it's positive or negative, the reflection about the x-axis. So if it's negative, it might cause it to flip on the flip from above the x-axis to below the x-axis if it's negative. So that one's the vertical stretch or shrink in reflection on the x-axis. This one right here, the B, on the inside of the parentheses, this is function notation, by the way. This F is function notation. This B talks about horizontal stretch, shrink. That's like the accordion effect that we talk about. And that's dealing with the reflection about the y-axis. The C on the inside deals with a horizontal shift. You might shift it left or right. And the D at the end deals with a vertical shift, shifting it up or down, whatever your function is. And what I'd say about all these things, what I'm talking about is my original function, y equals f of x. If you know what y equals f of x looks like, depending on what these numbers are, you have a stretch vertically, you might have a stretch horizontally, or a shrink, you might have a reflection, and you have a shift. So up to this one, A, the A right here, of course, is the amplitude. And we've already defined amplitude as max minus min divided by 2. The B on this one is the period. Likewise, this is just the shift, or sometimes we say the translation. This is shifting it horizontally, and this one is shifting it vertically. Causes a shift. I don't think I'm going to do a specific example. Well, I could do something on the calculator, I suppose. Let me clear these out. Let's just do a couple of this really quick. Let's say sine x. I want to tighten up my window a little bit, though. I don't want to be going so far. It takes too long. Let's go negative 2 pi to 2 pi. And I'll just leave it as negative 5 to 5. So there's my sine curve. Just as a quick review, if I were to put a number in the front of that, like 3 sine x, that causes the amplitude to go from 1 to 3. Amplitude, by the way, we think of that as absolute value of A, because you could have a negative there, because then it would cause, this probably should have been an absolute value here. Because if I put a negative in the front of that instead, if I did negative 3 sine x, what happens? Instead of going up, it goes down. Right? But the amplitude doesn't change. Picture getting kind of crazy. I'm going to clear that one. So there's that 3 on the inside. What if I take that out? What if I delete that, but I put a 3 on the inside? Now my period is going to equal 2 pi over b. There's my sine, my period is 2 pi. Now it's going to push it together, right? Kind of like the accordion look. My amplitude stays the same. My period on that one would be 2 pi over 3. If I wanted to stretch it, I would put something like 1/3 in there, I guess. 1/3 x. That would stretch it. Kind of slow. Sit and watch each one. So now the accordion, I pulled it apart. Maybe we should wrap up one last thing. This is a great day, huh? We need to talk a little bit about inverse functions. And all that means is we're going to work backwards to find the answer. We could take some time sketching these. We talked about inverse functions before where you do y equals f of x, and you switch it around. Y equals sine x, then we have x equals sine y. And if I want to get y, we write it this way. It's the inverse of x. Now, I'm just going to kind of be a little sloppy here. Here's our sine curve. Is your sine curve 1-to-1? No. Our sine curve is not 1-to-1. It does not pass the horizontal line test. So we restrict the domain to make it 1-to-1. And we restrict it from negative pi over 2 to positive pi over 2. You restrict it. So you're looking at quadrants 4 and quadrant 1. So if I ask my calculator, and I say, what is the inverse sine of 0.5? My calculator says 0.523. Remember, I'm in radians. Maybe we should just jump back to degrees just for the fun of it here a second. 30 degrees. That's pi over 6 radians, by the way. But if I said to my calculator, what is this if this is negative 0.5, and it says negative 30? But usually they're going to ask you the question. They're going to say, give your answer between 0 and 360. Then what would you say? You wouldn't say negative 30. You would say, thinking about reference angles, you're in quadrant 4. So you know that you are 30 degrees away from it, so you know you're at 330, right? This is all review, isn't it? We've had this, but maybe not all in 55 minutes or 50 minutes. This was more like 2 weeks. So we restrict our domain from negative pi over 2 to pi over 2 for the sine. Where would we restrict our domain for the cosine curve? I don't think negative pi over 2 to pi over 2 would work very well because it wouldn't pass the horizontal line test. Here we go from 0 to pi. So now if you ask your calculator the cosine, and I say the inverse cosine, but I get a negative, like negative, we'll go 0.5. It says 120. Where else would it be 120? I should have asked that about the sine as well. So now you have to think about what references to 120? 60. And what other quadrant is the cosine negative? 3. So what angle are we talking about in quadrant 3 if it references to 60? So you do 180 plus 60 and you get 240. We're doing stuff like this. Last year, you're, all right, I'm here. Well, I'm going to get another answer right there, correct? Because I'm thinking about the x value. The x value is negative, in this case, 0.5. So we restrict our domain from 0 to pi, or 0 to 180. How about the tangent? Anybody remember what you do on tangent? Our tangent curve looks like this. Is it clear that we can restrict our domain from right here to right here, which is pi over 2 to negative pi over 2? And you get all of your values right there. If you want to look in the textbook, we should maybe do that really quick at a couple pictures since we're running out of time. Turn to page 51. Page 51, they've got a couple pictures of some inverse trig functions for you to look at. The last one's the easiest one, I think, to understand, to see anyway. We just did the tangent. Top right, the top right on page 51 is the inverse tangent. You just take that one and turn it sideways. And the other ones are there as well. Should I wait till tomorrow to give you homework? Or do you want to start on it? I probably should give you something to start on. I think you should do 1 through 10 on the quick review. On the quick review, 1 through 10. And that's on page 52. I'll give you the written exercises tomorrow. If you want them, I guess, they're on my website. I am going to plan in some time tomorrow. We're going to need some time. Page 52. I'll read them to you just so you have them. 1 through 21 odd. 24, 25 through 43 odd. 44, 50 through 55.
Was it 25 through 40?
25 through 43 odd. And then quick quiz 1 through 4. It's on that next page, page 55. Quick quiz 1 through 4. But it is on my website. All right, so, wow, trig functions. And then some. We did quite a bit.